Section 4.5, Solving Initial Value Problems with Laplace Transforms. We have spent several sections so far this chapter familiarizing ourselves with Laplace Transforms and working through plenty of examples. And so we're at the point where we are prepared to put them to their intended use, to use Laplace Transforms to solve initial value problems. And actually, we've already done that. In section 4.3 in example 2, if you look back at the notes, I did an example where we solved an initial value problem, this one here. This was our differential equation. These are our initial conditions. And if you look back at that example, we worked through it and found the actual solution of that differential equation by taking the Laplace transform of the entire equation and then working through the necessary steps and eventually finding the inverse transform, which was our solution. So as I mentioned here, we got a little ahead of ourselves. I couldn't help it. I just wanted to do that example because I think it was fun. So in this section, there's really not much for us to do because we have accomplished the primary objective of this section in the textbook, which is to work through exactly this type of example. So what I'd like to do in this lecture is just work through a couple more examples that highlight some of the details that will arise in these sorts of problems, and that'll be it. Before we get to the examples, I do point out that the examples that we work in this section can be solved using techniques that we used in chapter 3, techniques such as undetermined coefficients or variation parameters. And for these examples, we don't need Laplace transforms, but Laplace transforms provide another method for solving this type of problem. And I point this out partly because in the next two sections, section 4.6 and 4.7, we will investigate differential equations that we cannot solve using techniques from chapter 3. There's two specific types. In section 4.5, the coefficients of our differential equation will not be constant. If that's true, the techniques that we used in all of chapter 3 cannot be applied. And then in section 4.6, we'll encounter the type of discontinuous functions that we just looked at in the last section, and so we will use Laplace transforms to solve those differential equations. But for now, let's take a look at a couple of examples and how we use Laplace transforms to solve initial value problems. Example 1. Looking at this differential equation, I acknowledge that this is the type of problem that I could have solved back in chapter 3. I can imagine using undetermined coefficients or variation parameters, but our purpose in this example is to demonstrate how we use Laplace transforms to solve this same equation. As we've seen previously, I will take the Laplace transform of the entire equation. And as we know, when I take the Laplace transform of a sum of terms, such as I have on the left, I can take the transform of each term individually. I also know that coefficients will come outside of the transform. So when I take the Laplace transform of this equation, I think I get this equation here. On the left-hand side, to take the transform of y double prime, we have a theorem from a couple sections back that tells me what that transform will be. Here's the result of that theorem. If I take the transform of an unknown second derivative, I get s squared times the transform of the unknown function, which I'm calling here just capital Y, minus s times, then these, as we've seen previously, are these initial condition terms. A similar theorem allows me to evaluate the transform of y prime. And then the transform of y, I will once again just write as capital Y. And on the right-hand side, I have the Laplace transform of cosine, which is a function I'm very familiar with. So I can just state directly that that transform is s over s squared plus 1. At this stage, I can plug in the specific values for these initial conditions that were provided in the problem. And then my goal is actually to isolate capital Y. So I see several terms on the left-hand side that have capital Y's in them. These other terms that do not, I will push over to the right-hand side. And I'll actually factor the capital Y out of the terms on the left at the same time. And as I've pointed out previously, this quadratic that acts as the coefficient on capital Y is exactly the characteristic polynomial of the homogeneous version of my original differential equation. And that is not a coincidence. That should always happen. Next, to isolate capital Y, I simply need to divide by that characteristic polynomial. And now I arrive at what is often the most difficult part of these types of problems, doing partial fraction decomposition. So I have an expression for capital Y. So in theory, if I could take the inverse transform, that would give me the solution to this differential equation. Unfortunately, these fractions that I have now are not yet in a form that I recognize. So I need to do whatever algebra is necessary to get these fractions into a form which I can easily invert, or the inverse of which I can easily recognize. And as I mentioned, this often involves partial fraction decomposition, completing the square, the types of algebraic techniques that we've seen demonstrated over the last several sections. Here off to the side, I've worked through the steps required to perform partial fraction decomposition on this second fraction. Again, there's different techniques for completing partial fraction decomposition, and I'm not going to walk through the steps here, but maybe you can take a look at the completed notes for reference and just verify that you can follow along with my steps here. Based on this partial fraction decomposition, I'll rewrite this second fraction. And then let me just make a couple comments. This second fraction I can break into two separate fractions, basically s over s squared plus 1, and then a constant over s squared plus 1. And so I recognize those as the transforms of cosine and sine respectively. I will have to accommodate for these coefficients, but I'm pretty much ready to find the inverse transform of this fraction here. And then it's also worth noting that this first fraction and this third fraction are actually like terms. So I can combine those. They have the same denominator. I can combine them by adding, and then that will leave me with just a single fraction. And now I'm almost ready to find the inverse. With this last fraction, I do have to deal with this denominator, and unfortunately, this denominator will not factor. So I'm going to need to complete the square on this denominator, and as we've seen in recent examples, that'll force me to do some modification to my numerator at the same time. So let me try to do all of that in one step. So here I have completed the square in the denominator, and then I have modified my numerator in such a way that the numerators of these two fractions match up with what they would need to be in the structure of these Laplace transforms. So I finally have capital Y in a version which I can directly take the inverse of. Each of these fractions of s is a Laplace transform that I recognize. I, of course, do not have enough room here at the bottom of the page to write my solution, so I'm going to slide up over here and write my final solution. So here I have my final solution written in pink in this orange box. Looking through term by term, I recognize this as being the transform of cosine. This fraction is the transform of sine. And then on each of these two fractions, I have s over s squared plus 1, but since s minus 1 is acting as the variable here, then I have to multiply the corresponding inverse transform by e to the 1t. So that's where I get these e to the t cos of t and e to the t sine of t terms. Looking through all of the work that was required in this problem, I definitely acknowledge that using Laplace transforms was not a direct and quick method for solving this differential equation. But I would remind you of what the alternative would require. Since we have a non-homogeneous differential equation, if I wanted to use undetermined coefficients, for example, I would need to first find my homogeneous solution, then postulate a form for the particular solution y sub p, then do necessary algebra to solve for the coefficients in that y sub p. And even then, I wouldn't be done because I would have to take additional steps to incorporate the initial conditions. So in a certain sense, one advantage of the Laplace transform technique is that it incorporates all of those steps into one method. We have already accounted for what the non-homogeneous term does to this differential equation. We have already solved for our coefficients. We have already incorporated initial conditions. And so all of those steps are accomplished in one method. Again, I acknowledge that there is a lot of work to do here, but I just wanted to point that out as sort of one potential advantage of this technique. All right, I want to take a look at one more example. In example 2, we have a homogeneous differential equation. So I have a 0 right-hand side. And then in this particular case, the initial conditions, y of 0 and y prime of 0, are given as generic parameters. They're represented here as the variables capital A and capital B. So let's go ahead and get started by taking the Laplace transform of this entire differential equation. Here are the first few steps of my solution. I've taken the Laplace transform of the entire equation. Because of properties of the Laplace transform, I know that it breaks down into the Laplace transform of the individual terms. Each of these Laplace transforms is something that we have familiarity with. So taking the Laplace transform of each term wasn't too difficult. And then as usual, I'm going to try to isolate capital Y. On the left-hand side, I have this coefficient function, which perfectly matches the characteristic polynomial of my differential equation. And as I've mentioned, I expect that to happen. And then these terms, which do not have capital Y's in them, I've pushed over to the right. And then in this particular problem, we're not given specific values for y of 0 and y prime of 0. Instead, we want to represent them as these generic variables, capital A and capital B. So I've made those substitutions as well. So if I divide by this coefficient function, I will have an expression for capital Y. And in theory, I can take the inverse transform at this point, but I need to do a little bit of algebra to get this fraction into a form that I recognize so that I can state the inverse directly. In this particular case, I can't do partial fraction decomposition because my denominator does not factor and my numerator is already 1 degree less, and so there's no additional simplification that I can do. So I think instead I'll focus on completing the square in this denominator. So now that I've completed the square on this denominator, I just have to manipulate my numerator so that the structure of the resulting fractions will be what's necessary in terms of known Laplace transforms. So just to clarify this process a little bit, here I just want to talk through how I approach this type of problem. First of all, my numerator is AS plus A plus B. So whatever modifications I do to the resulting numerators down here, I have to always reconcile them with what my numerator actually is. In the first fraction, for example, since I have s plus 1/2 quantity squared, if I want this to be of the cosine form, where the numerator is the variable s and the denominator is s squared plus some constant, then these, what's acting as the variable here, as along with the numerator, have to match. So what I've written here is what I need. What I do next is simply imagine actually foiling out the expression that I have and figure out what's missing from that expression. So in this case, since this a has been brought down as a coefficient, if it was distributed through, I would have a times s plus 1/2 times a. In my actual numerator, I've got a times s plus 1a, like a full a. So this numerator is missing a over 2. I'm going to write that in pink over here so that I have it for reference, but I don't think I'll actually include it there as part of this numerator. Let me see what's going on with this second fraction before I decide exactly what I have to do with this 1/2 a. This second fraction has the general structure of the transform of sine because there's a constant in the numerator and then effectively s squared plus some constant. Once again, I have s plus 1/2 acting as the s squared, or acting as the s. And then in order to get this to align with the structure required for the transform of sine, I need to remember that this constant here is actually something squared, and the numerator needs to match the square root of that. So my numerator needs to be the square root of 3 over 4. I've written that here as root 3 over 2. So now I once again look at what my numerator actually is and think about what terms I need to introduce or modify here to make this numerator match the numerator that I actually have. And in this case, I have a plus b, but I don't have this square root of 3 over 2 times those. So to accommodate that, I can multiply out front by 2 over root 3. So now putting all of this together, I think I can accommodate for the fact that I'm sort of missing a 1/2 a here by simply making this 1/2 a. Let me imagine what would happen there. When I distribute this a through, I would have as plus 1/2 a. in this numerator. Once I distribute this square root of 3 over 2 to this fraction here, that cancels those, and then I would want to add 1/2 a plus b. So I'm going to indicate that here. I'm being a little lazy, but I've crossed out this 1/2 a that we didn't have a place for earlier. I just want to indicate that my function here actually has a 1/2 in front of this a. So I think I'm ready to find the inverse transform of this capital Y. So here is the solution that I get. And let me just take a quick second to interpret the structure of this solution. Looking back at my original differential equation, one way I could interpret this differential equation is as representing a mass spring system. And if you look back at the examples that we discussed in that context, you may remember, you'll see that the coefficients have specific physical interpretation. Namely, the coefficient on the second derivative is the mass, the coefficient on the first derivative is the coefficient of friction, and the coefficient on the function term is the spring constant. So one way we could think about this differential equation is as modeling the mass spring system where all of my parameter values are taken to be units. They're taken to be exactly +1. So maybe I can imagine I have scaled my units in such a way and I've chosen exactly the right mass so that all of those parameters are exactly 1. From that perspective, y of 0 would be like the initial displacement, and then y prime of 0 would be the initial velocity. So one way to interpret our solution is the behavior of the mass under the circumstances in which the units are chosen in such a way that each of my parameters comes out to be exactly +1. And then the capital A and capital B represent these additional properties of the system. And so as I look at this solution, I can kind of identify what role those capital A and capital B, or the initial displacement and the initial velocity, play in my function. Looking at this solution, I recognize that there is decaying oscillation. So we would say that the system is under-damped. That is to say, if you do pick a system such that all of your parameters are exactly the same, you will get decaying oscillation, as indicated here. And then note that the coefficient on my cosine term is exactly a. So the coefficient on the cosine portion of my solution will be exactly my initial displacement. And if you think about the form of a cosine curve, it always starts at its maximum point and then decreases. So it kind of makes sense that my initial displacement determines the amplitude of this cosine term. The coefficient on my sine term is much more complicated. So there's no direct interpretation of the influence of the initial position and the initial velocity on this sine term. So none of this reference to the mass spring system was directly stated in the problem, but I just wanted to provide that perspective as another way of getting a little bit more information out of our solution. That wraps up section 4.5. In this section, we used Laplace transforms to solve initial value problems. And the two examples that we saw were problems that we could use other techniques to solve. In the next two sections, that's no longer true. We're going to briefly look at two types of differential equations that we could not solve using techniques from chapter 3, and that we must therefore solve using Laplace transforms.